Okay, here we go. Well, we come back and let's discuss this theorem that we wanted to prove last time. What we're trying to prove here is if you have product of two spaces, then the product itself, the space is going to be compact precisely when each coordinate space is compact. And we said that to prove that theorem, we'll need a tube lemma. That's a very interesting lemma telling you if you're working on a product space, you pick one element of the first space, and you take a neighborhood of what we call the slice at x0. So that's a space homeomorphic to y, but inside the product. Then for any such open set containing this guy, in case you assume y is compact, you can cook up what's called the tube neighborhood inside of your neighborhood A. So that's what we did last time. And the idea for today is at some point we should use that to prove our theorem 2 from last time. So theorem 2 from last time is over here, namely product is compact precisely when each coordinate is compact. So let's write the proof for theorem 2, because the tube lemma has been proved. So I think I said this before, this direction of theorem 2, if you assume x cross y is compact, this should be the easy direction because we know that any continuous image of a compact space will be compact. So assuming x cross y is compact, we have continuous projections. The projections from the product x cross y to x, let's call this maybe px, and py from x cross y to y. Since these guys are both continuous projections, we just can be sure that x and y are compact, because we know any image of a compact space under a continuous map is going to be compact. Okay, so that was the easy direction. I see there's a question in the chat. Yes, so there's a question of what compactness is. What compactness, we defined that like 3 lectures ago. The idea is whenever you have an open covering of your space, you will always you can always hook up a finite subcover. So yeah, that's the definition. But here we're not really using the definition, just building on theorems that we know. So other direction here. Now let's assume x and y are compact. And of course, we need to use the tube lemma. So we want to show x cross y is compact. And how do we prove something is compact? Let's take an open cover. So take an open cover. Of x cross y. So let's call this open cover, maybe it's called W i's, where that's supposed to be an I, where I lives in some index at lambda. And now the idea is we want to use the tube lemma. So for each point on the first space, each x in x, we have this space sliced at x, right? Which is a subset of x, entire x cross y, which is the union of the wi's. So we have this subspace, which is inside the union of these open sets. But this guy, as a space, is just homeomorphic to y, which is compact. So, but x cross y is homeomorphic to y, homeomorphic to y, which is compact. And just from there, we can be sure that X cross Y is compact. So if we have a compact space, this guy is compact, and we have this inclusion here, we have an open covering. So X cross Y is inside the union of the WIs, but it's compact. We know that there are finitely many indices. So we know there are, maybe instead of using indices, let me use a subset. There is a finite subset that's going to cover the slice. But the subset will depend on the fixed X that I have here. So I have a fixed X. So the subset will depend on X. And the very important thing is that it is finite. This is crucial. So we have a finite subset that's going to cover the slice. So X cross Y is actually going to be inside this finite union. Just take indices in IX. Sorry, that should be W's. Are we okay so far? Okay, so now we have this finite cover, and let me call these guys n of x, because I want to use my tube lemma. So this is just notation, calling this union n of x. So let me go up to the tube lemma. Here's the tube lemma. That says you have a product space where y is compact, and you fix a point, and the neighborhood of this slice. Then you can hook up a point, a neighborhood of the point, sorry, such that the tube is inside the neighborhood. So this is what we want to grab now. So let's grab that. Since y is compact, and n of x is open containing the slice, x cross y, by the tube lemma, we know that there's a tube inside the neighborhood. There is some open set in x. So the open set in x will now depend on little x. So some open use of x in x such that we can sandwich the tube inside of it. So such that the slice is actually inside the tube, which is inside n of x. So the important thing here is the existence of this guy. Any questions? So far, I'm not really using that this guy is finite. I could have just used the entire lambda, but for a very good reason, I need this guy to be finite. Okay, so now that we're here, that's just using the tube lemma. At some point, we need to use that also x is compact. So here's how we use that x is compact. So this works for any little x in big X. So that means, so there's another question in the chat asking, how can we use the tube lemma to know that u of x is open in X? The tube lemma tells you exactly that there exists an open set u. So this is the tube lemma. There exists an open set u. So it's not, we're just applying the tube lemma. There's no weird interpretations, just literally the tube lemma. Is that okay? Okay, let's move on. So this works for any x. Our annual space x is compact. So we're just going to use all these ux's to hook up a cover. So these guys here, u of x, where x is any element in the space x, they form an open cover for x, the space x, which is compact. Right? So it's absolutely clear that our x, what I'm saying here is that x is going to be the union of all these ux's. And both inclusions are for free. This one is because each little x lives in u of x, and the other inclusion is for free because each u of x is a subset of x. Now, we use that x is compact. Since big X is compact, we know that this covering will admit a finite subcover. So there is a finite set, let's call it A, inside of X. So this is A should be thought as an index set, not a subset of the space. So finite set A such that our X is actually just going to be the union of these guys, U of X, but where X moves on a finite set A. Okay, just using definition of compactness. And now we're almost done. Therefore, when we do x cross y, what we're going to have here is, instead of x, I can write the union over a of u of x cross y. And this is very good because I can distribute the union here. So this is going to be the union over x of a in a of u of x cross y. This is going to be a subset because each u of x cross y is a subset of what we call n of x. And remember, n of x, when you go up, it's not a weird thing. It's just this guy. It's a union of finitely many wi's. So this n of x is just the union of finitely many wi's. So maybe I can continue here. N of x is union over x in a, union over I in ix, wi. Because n of x is exactly this guy. N of x is exactly this guy. And the good thing here is this union, these two sets are finite. So the union is finite. And that means we have a finite subcover. Thus, the cover wi is where I lives in lambda and it's a finite subcover. And we're done. This means that the product is compact. Okay, any questions? Okay, I think this is a neat proof. Once you have the tube lemma, but it's remember the tube lemma wasn't free, so it's kind of surprising that we need all this work to show that the product of two spaces is compact if each space is compact. So it's kind of surprising. Let me say something. The elephant in the room now is what about infinite products? So let me just say this theorem still holds for infinite products. but with the product topology. The box topology will not work. The product topology. So this is kind of a famous theorem. This is called Tychono's theorem. You can find it on chapter, let me find it. You can find this theorem chapter 5. Of course, the easy direction is just the same. The problem is the backwards direction. That's the one that needs some work. Okay, any questions about this argument?
Yeah, so I get I get what you're doing in general, where the back half you use the tube theorem, you take the function nx and then you take like a subset. But I'm a little confused on the section where you say, okay, so we have ux cross x is a subset of the union of nx. Can you re-explain how you got to that point?
U of x cross this part?
Yeah, I'm just confused because it's just weird because we define nx. Don't we define ux in the function n or something like that?
So if you forget about the union signs here, sorry, if you forget about the union symbols, for each x, this inclusion follows exactly, so this inclusion follows exactly by the tube lemma. That's what the tube lemma claims to is trying to do for us. So let me go up. For each x, we have this. For each x, we have that inclusion. Now, if you take the union over A, well, you still have same inclusion because each term is a subset of the other. Is that okay?
That makes sense.
Any other questions? Okay, so that's uh, that's the proofs of this very interesting theorem. You can also go check out the proof for Tychono's theorem if you're interested in this sort of arguments. I think it's also instructive, but not that much. What I want to do now is I want to, at some point, we need to discuss compactness in the real time. So let's discuss this now. So we started this discussion. So the very first class we discussed compactness, we proved uh, pretty much any interval that you can write, A, B. Now let's say you have like close at A, open at B, or the other way around, open at A, close at B, or maybe you could have negative infinite A, maybe you could have negative infinite closed at A. You could also have A infinite, or you could have closed at A infinite. These guys, and also the real line, all these guys are not compact. So we proved all those guys are not compact. Very different from the connected situation, or those guys were connected. And we claimed, with no proof, the closed interval AB, closed and bounded, is compact. I never proved it. So that's our theorem now. Theorem 1 for today, because the other one was from previous class. So for let's write a nice statement here for any A smaller than B, the interval A comma B inside of R is compact. So we need to prove this. So the idea for the proof is going to be something like this. Let me just start with the proof and then I will tell you the idea. So because the idea depends on the open cover. So let's take U, some collection of open sets UIs. So open sets in the real line. which contain AB. So which cover AB, sorry. So we start with an open cover, and what we want to show is AB admits a finite subcover of this U, finite subcover of U. Namely, we can cover AB instead of using all of them, just using finitely made. So what's the idea here? It's going to kind of be similar to the proof we did in the connected scenario. So the clever idea is that we need to consider this set here. The set, let's call it C. It's going to be all points in this semi-open interval. I need to be open at A because otherwise, for a formality, the proof will make no sense, but it's not very important. But I want to take all points such that AX admits a finite subcover. Maybe I need more space. It's finite subcover for this fixed cover here. So what's kind of going on is the following. This cover U is given. So this cover U here is given. We know that AB is inside of the union here. So for any such X, AX will be inside the union. But we want to take only those X's for which we can be sure that we have a finite subcover. So the scenario will be something like this. Here's our A, maybe. Here's our B. And what we're taking in this set is points X such that this portion is covered by finitely many UIs. So we're only taking those X's. And the idea here is kind of, we want to push X all the way through B so that we know AB is going to be compact. So of course, we cannot say, well, X is going to be B, but what we can do is take the supremum of this set, because we want X to go bigger, and prove that the supremum needs to be B. So that's the idea. So the idea is C has a supremum, and it needs to be B. If we prove this, then we'll be done. Because that will mean B, the supremum, maybe I should say, needs to be B which lives in C. Because if, in that case, that would be tell us A comma B admits a finite subcover. So we need to prove like three things. Has a supremum, the supremum is B, and it lives in C. Maybe first we'll show it's B and then it lives in C. Okay, so how do we do these things? Well, we'll go by steps. So any questions before we start proving the steps? So we cannot assume AX admits a finite subcover. But it's a very good question because that's the first step. I'm on this set C, I'm only considering points for which this guy admits a finite subcover. So it's a very good question. Is there any such X doing that? That's a very good question. So that's the very first claim we need to prove. Claim one, C is not empty. C is not empty. And not only that, it admits an upper bound. And as a consequence, this we will need to prove. If you prove it's not empty and admits an upper bound, hence it has a supremum. Hence it or maybe let's say C as a supremum that we will call S. That will be the supremum of C. But yeah, it's a very good question. How can we assume AX admits a finite subcover? We really cannot. So how do we prove that C is not empty? So let's prove claim one. To see that C is not empty, we cannot say the easiest thing here would be take X equals A, but we are not including A on C. So that's not a very good idea. However, we're almost there. So to see that C is not empty, we note that our initial point A, it lives in AB, right? So I'm trying to kind of show there is such 1x of this. So this guy lives in AB, which is inside the union of these guys, right? That's the open cover we started with for AB. And this means that there must exist some index, let's call it J, some index, such that the corresponding open will contain A. And now we can use that Uj is open. Since this Uj guy is open, we know that there exists some positive epsilon such that not only A, but the entire A minus epsilon, A plus epsilon is inside Uj. So why are we doing this? Because this is the picture here. Here's my A, here's my B, not important at this point, B. So what we're saying is some Uj, which is open in the real life, will contain A, but it's open, so it will contain an entire open interval, something like this. A minus epsilon, A plus epsilon. Okay, and then this guy is Uj. Maybe let's use the Uj for H. So this guy is open here. But if you take, for example, this point, so here we have A plus epsilon over 2, and you can take it closed, then this entire closed set is inside Uj. And then we're done. Because, let me write them. So in particular, maybe let's move this over here. That's the picture. Hence, the entire closed interval A to A plus epsilon over 2, and now closed, is inside of Uj. So this x, if we take this as x, then we go out to the definition of C, we're trying to take points such that the close admits a finite subcover. So this guy admits a cover by just one set. This is, of course, finite subcover. This is just covered with one element. So finite subcover, just using one set. Thus, what we have is that A plus epsilon over 2 lives in C for this epsilon that we know exists. And that means that C is not A. Are we okay? just proving C is not empty. Okay, we're not done with claim one because we also need to show C has an upper bound. So how do we show C has an upper bound? Well, that's not complicated. By definition, C is a subset of A comma B. Now, since by definition C is inside open at A, close at B, we know that B is an upper bound. For C. So this part is not complicated, and that's the end of claim one. And the upshot here, or what we deduce is we have a supremum. Hence, there exists S, the supremum of C. Any non-empty set that's bounded will have a supremum. That's property or an axiom of the real numbers. Okay, any questions? So now the idea is we built this guy here, and we somehow want to push it. So the second claim, this is the kind of delicate one. Claim two is that the supremum actually lives in C. It's not always true that the supremum of a set lives on a set. In the set, it's usually just a real number. Could live or could not live in C, but here we want to show it lives in C. So how do we prove it lives in C? Well, the idea will be we need to do two things. So first, remember things in C are things that lives in this interval, open at A, close at B. And then we need to show something else, but this is the first claim. So why is it true? No. Why is it true that A is smaller than S? Well, that A is smaller than S, remember S is the supremum. So to show this, well, we can just use our previous epsilon. So this follows from, or maybe using the epsilon that we built before. And why does it follow from that epsilon? Because for that epsilon, we showed that A plus epsilon over 2 lives in C. That's exactly what we showed. And then, since S is an upper bound, for C, we have A plus epsilon over 2. That guy is always bigger than A, and it's smaller than or equal to C, because C is an upper bound. So A is smaller than C. So that's the first part of this inequality. We also need to show that S is smaller than or equal to B. So this other inequality, S smaller than or equal to B, to show that S lives here before B. This follows because B is an upper bound. That's what we said before. B is an upper bound for C. And S is the smallest upper bound. So that's all we need to say. Any questions? So let me write right here what's our C. So these are points in open at A, close at B, such that AX admits a finite subgroup. We only showed that S satisfies this very first condition. Now we need to show this. So second, maybe I can use another green for this. Second, it's still the same claim. We show that the entire set interval from A to S admits a finite subgroup. And this is the complicated part of this claim. Because S is now this very particular element. Are there any questions so far? So what I'm going to do is something very similar to what we had before. Here's my A, B. Here's B. Here's A. I don't really know where S lives. Let's just say it lives somewhere over here. Maybe let's keep the same color. My S lives here. So I do know A is bigger than S is bigger than A, smaller than or equal to B. So let's use that. I will build on this graph. Since S lives in A, B, which is inside the union, inside this open cover, what we know that there must exist some open that will contain S. That exists some, let's use K in lambda such that S actually lives in UK. And now we're going to use that UK is open. But UK is open. So there exists some new epsilon, but I'm just going to stay with same notation, some epsilon bigger than 0, such that not only S, but S minus epsilon, S plus epsilon lives inside of UK. So what I'm doing in my graph is something like this. Here's S minus epsilon. Here's S plus epsilon. And what I can be sure of is that this UK, whatever that is, will contain all these parts. Epsilon should be smaller, but I'm trying to make drawing kind of precise. So this is what I'm doing. So are there any questions at this point? Okay, so the idea is at this point that we know S is the smallest upper bound. And we want to somehow deduce that to show that this guy here admits a finite subcover, it's only enough to show that at some point here, this guy admits a finite subcover, because whatever remains, you can cover it with this extra UK. So we just need to look up something here. But the only problem with this is it's really not a problem, but this guy could be in principle on this side of the interval, and that will be problematic, but we can just assume that's not the case by shrinking epsilon. So by shrinking epsilon, we can just, moreover, we can just assume, and this would mean otherwise you can shrink epsilon, maybe let's say, moreover, since A is smaller than S, we can assume that A is still smaller than S minus epsilon. So what I mean is, with this, what I mean is we have this sort of situation. Otherwise, if your A will be here, you can like just take smaller epsilon and do the same stuff. Okay, so now what do we do with this S minus epsilon? We're very close, because this S minus epsilon is smaller than S, which is the supreme of C. So what we get is that S minus epsilon is not an upper bound. It's not an upper bound because it's smaller than the smallest upper bound. And if you are not an upper bound, that means there is something in the set that's bigger than you. So that being the case, we can be sure that there exists some D in the set C that's bigger than S minus epsilon. So how do we write that? Bigger than S minus epsilon, but at the same time, smaller than or equal to S, because S is the supreme. So my D will live somewhere over here. And what I'm saying is this guy cannot be an upper bound. So there needs to be some D in C. And if you live in C, you are also smaller than or equal to S. Are we okay with this? So what's the crucial part now? But then since what we can do now, but then my interval A to S, remember I want to show this guy admits a finite subcover, and then these guys will admit a finite subcover because of the following. Maybe let's take first. And then since D lives in C, by definition, we know that this guy, A comma D, admits a finite subcover. And that being the case, you don't need therefore, if you go instead of all the way to D, you go to S. You can just say this is the same as going to D, and then to S, which as we're saying here, we can do the finite subcover for this guy, and this guy is entirely inside our UK. So finite subcover for this, an extra one for this guy will also admit finite subcover. And that's exactly what I want to show. So that's exactly what I want to show, that S lives in C. And that's the end of thing 2. Any questions? So here's the picture again. What we're doing in the picture is something like, we want to assume all the way through S, you admit a finite subcover. The very important hint is S lives in some UK, and then that UK will contain an entire bunch because it's open. Now, there needs to be something here in your set C, because this guy is smaller than the smallest upper bounds. And if you live here and in C, then this guy admits a finite subcover, and then also this entire thing admits a finite subcover because we have an extra one. Okay, let's prove the last part of this theorem of this proof is claim 3, which tells you that the supremum is actually B, as big as it could be. So to prove this, what we know is we prove that S is smaller than or equal to B. So that is not perfect. So if you assume for a contradiction that it's actually smaller, strictly smaller, so if you assume S is strictly smaller than B, then we go up to the picture. In that case, we can, so this we never knew where S plus epsilon lives. Could be over here. But if S is actually smaller than B, you can be sure by shrinking epsilon again that this S plus epsilon is also smaller than B. So let me write. So assuming for a contradiction that S is smaller than B, in the proof of claim 2, we can just shrink epsilon. We can take epsilon such that not only it does what it does, moreover, such that S plus epsilon is smaller than B, just shrinking it again. And now in this case, our entire S plus epsilon half will be inside UK, because the entire S plus epsilon open lives in UK. So if you close it at half, you live inside UK. And that means when you go from A to the supremum plus epsilon halves closed, you have AS union S plus epsilon half. We just proved this guy emits finite because S lives in C. So we prove this guy emits finite. That's claim 2. And this is just contained in UK. So also emits finite. Emits finite subgroup. And that being the case, what you get is that S plus epsilon over 2 lives in C. And this is very problematic because S is an upper bound and S plus epsilon over 2 is larger than S, which contradicts that S is an upper bound for C. And this contradiction came from assuming that S is smaller than B. So this proves claim 3. In other words, what we proved, let's summarize the proof, as B, which is the supremum of C, we prove lives in C, which is points X, such that AX admits finite subgroup. In other words, if B lives there, therefore A comma B admits a finite subgroup. And that's what we want to prove. So that's the end of our proof, which was quite a bit of work. Are there any questions? I will give you like 10 seconds sorry, I will give you like 10 seconds to think about this. Are there any questions? Okay, I don't think there are any questions. So let me tell you why this theorem is important. Well, it's important because we wanted to know that closed interval AB is compact, but also because, for example, uh, there is the extreme value theorem in the reals. So something like this is from analysis. So this is the extreme value theorems. Extreme value theorem. That's telling you if you have a function from AB to the reals, so they should be closed, is continuous, then it will attain the maximum and minimum values. Then there are some points, exists x min, x max in AB such that f at x min is going to be smaller or equal to f of x, smaller or equal to f at x max. And that's for every x in AB. And that's just the consequence of the interval AB being compact. That's what we're going to discuss next class. Are there any questions?
Yes, I have a question. I kind of get the general idea of this like theorem because the way I think about it is that